Dr. Triranjita, everyone associated with the Kalindi College, all faculty members and students. It's my great pleasure to be participating in this important seminar on exploring physics for the benefit of students, not only of Kalindi College, but for all those who are participating in this workshop. Going beyond the classroom is a very important thing for any college, and knowing what all going on other than the curriculum is of great relevance and great importance for the student. Such workshops play a very important role in the growth of the academic community, particularly the students of colleges. So I'm extremely happy that Dr. Pushpa Bindal and Dr. Seema Gupta have taken this initiative in organizing the workshop. And in the past also, they have organized several workshops, and Kalindi College has been really very active in organizing such workshops, which I'm sure is of great benefit to student community at large. And with the technology that we have, namely this technology, not only it benefits the students of Kalindi College, but not only students in Delhi, but throughout India. In fact, there can be, in principle, participation from the entire world. That is the beauty of technology that we have with us. And it is for us, teachers and students, to use this technology wisely. I will say a few words about the National Academy of Sciences India. Maybe Professor Anurag Sharma will also speak on that. This is the oldest science academy, and it was started in 1930 at Allahabad, which is now known as Prayagraj. And, most students may not remember, we were not even independent at that time. So getting money to start with, Professor Saha and his colleagues started this academy to have interaction, to have a general awareness of the masses, of the advantage of science, of the role that science and technology plays in our day-to-day life. And it has become
this particular mandate, and we keep organizing these kind of activities. We also support some small student projects. In the past, they have been done, and we continue to do so, where the students are mainly involved, guided by college teachers or school teachers, and some modest amount of money can be given for supporting such activities. Interaction with school students, as I said earlier, is also one of the mandates, and we would like more and more college teachers to sort of engage in that particular activity. So these are the gamut of activities which NASI is mandated with, and Delhi chapter goes along with these particular activities. So this is also one of the activities like that. Last month we had a good workshop on virtual experiments, and this is which was also done by Kalindi College, and this is again being done by Kalindi College. So I would like to thank the Kalindi College administration and congratulate the organizers that they are able to do such good seminars and workshops. So thank you very much to all of you for having joined. I'm sure most of you will benefit from these activities. Thank you.
Thank you, sir.
Thank you, sir. Thank you so much. Thanks for your encouragement and support, sir. We are really thankful to NASI to believe in us and ready to be associated with our projects. Thank you, sir. So now we start with the first session of the national workshop. So first session for today is the Fiber Optics Revolution by Professor Ajoy Ghatak. It's my privilege to introduce Professor Ajoy Ghatak. Professor Ajoy Ghatak is a renowned Indian physicist and author of many physics textbooks. He is currently Professor Meghna Saha Fellow of National Academy of Science, India. His research interests are in fiber optics and quantum mechanics. In recent years, he has taken a keen interest in bringing the genius of Albert Einstein to the wider public and was invited to present a TED Talk, Inside Einstein's Mind, in 2017. Professor Ghatak has written over 170 research papers and more than 20 books. His undergraduate textbooks on optics and his monograph on inhomogeneous optical waveguides has been translated to Chinese and Persian. His other books include Quantum Mechanics, Theory and Applications, Fiber Optics, Optical Electronics and Lasers, and a popular book on Albert Einstein, The Story of a Genius. In 1995, he was elected Fellow of the Optical Society of America for distinguished service to optics education and for his contribution to the understanding of propagation characteristic of gradient index media, fibers, and integrated optical devices. Professor Ghatak received his master's from Delhi University and PhD from Cornell University, USA. He joined the Indian Institute of Technology, Delhi in 1966 and retired as an emeritus professor of physics at IIT Delhi in 2007. He is the recipient of many prestigious awards, which include Shanti Swarup Bhatnagar Prize for Science and Technology, Physical Sciences, 1979, by the Council of Scientific and Industrial Research. Galileo Galilei Award, 1998, by the International Commission for Optics. Esther Hoffman Baller Medal, 2003, by the Optical Society of America, and SPIE Educator Award, 2008, in recognition of his outstanding, unparalleled global contribution to the field of fiber optics research and his tireless dedication to optics education worldwide. It's our honor that today we have Professor Ghatak with us and we have another chance to listen to him. Professor Ghatak, I stop sharing my screen.
Thank you. Thank you, Seema. Shall I share my screen?
Yes, sir. You can now share. I have stopped sharing my screen, sir.
Can you see my slides?
Yes, sir. Your slides are visible.
Okay. Thank you, Seema. Thank you, Pushpa, for inviting me to this important workshop. I'll be speaking on the fiber optics revolution, but before that, I will tell you a bit about optics because the title of your workshop is exploring different aspects of physics. So I thought that I will spend a little time on the importance of optics and photonics. So the photograph that we have on the first slide shows a red laser beam guided through an optical fiber, which was fabricated at the Central Glass Ceramic Research Institute in Kolkata. So I would like to spend a few minutes to tell the students, these are all very simple concepts, why study of light has become so important. UNESCO declared 2015 as the International Year of Light. Why 2015? Because 1,000 years before that, in 1015, Alhazen, who was in Mesopotamia, now which is in Iraq, wrote the first book on optics, which was entitled Kitab al-Manazir, which was the first book on optics. This photograph shows the cover page of a translated edition of Alhazen's book on optics. In proclaiming 2015 as the International Year of Light, the United Nations recognized that applications of light science and technology are vital for existing and future advances in medicine, energy, information and communications, fiber optics, agriculture, mining, astronomy, architecture, archaeology, etc., etc. Then in 2018, UNESCO declared May 16th as the International Day of Light. Why May 16th? Because the first successful operation of the laser was done by the American physicist and engineer Theodore Maiman on 16th May 1960. As all of you know, he first produced the first laser, in fact, a first ruby laser. And in his hand is shown the ruby laser that he had first fabricated in 1960. And as we all know, the discovery of lasers has led to tremendous benefits of society in communications, healthcare, and many other fields. And one of the main advantage of the laser beam is its high directionality. If you have a light bulb, it radiates energy in all possible directions. But on the other hand, focused to a narrow spot. So here is a 2 millimeter wide, 2 milliwatt laser beam being focused at a focal of a lens whose focal length is about 2.5 centimeters, so which is about the focal length of your eye. So if you use the red laser beam, then the area of the focused spot is about 7 into 10 to the power of minus 10 meters square. And if you have a 2 milliwatt laser, then the intensity will be 3 megawatt per square meters. Such high intensities will damage the retina. So never look into a seemingly innocent low power laser beam. So the point that I'm trying to make is, whereas it is safe to look at a 1,000 watt electric bulb, but it is very unsafe to look at a 2 millimeter directed laser beam. And because focused laser beams produce extremely high intensities, it results in very important devices for the industry and also defense. Here is a laser beam drilling through concrete. And this particular photograph is from RR-CAT in Indore, Raja Ramanna Center for Advanced Technology. And therefore, a fiber laser can be cutting through steel. And as you all know, laser beams are now extensively used for eye surgery and in numerous hospitals throughout the world. And powerful laser beams can create temperatures. Focused laser beams can create temperatures of the order of fusion power. Right now, the power that is input that is required to create the laser beams is slightly more than the power that is created. But we are hoping in about a few years' time, it will be the other way around. That is, the fusion power that is created is more than the power that is required to have the large number of laser beams. And when that happens, you will have a fusion reactor in this slide. I don't know how. Then, the 2018 Nobel Prize in Physics was awarded for groundbreaking invention in the field of laser physics. So laser physics has become extremely important even as far as basic physics is concerned. And half of the prize money was given to 92-year-old Arthur Ashkin, who passed away only a few weeks back, for his contribution to optical tweezers and their applications to biological systems. So this is a tweezer holding a diamond, small diamond piece. This is actually, so you want to trap a virus or a large thing which is about a millimeter in bead, in a millimeter in diameter. And so that is the concept of the optical tweezer. And that is based on the principle that light that is emitted, which was put forward by Einstein in 1905, radiation is emitted in discrete 1.53, 1.54, 1.545, and so on, hundreds of wavelengths. You have a large number of wavelengths passing simultaneously through a hair-thin fiber, getting amplified by the alpha. And then there is something to compensate for the dispersion also, which I have not done. Everything cannot be done in 1 hour. And get many areas in Gurgaon where they say that they have fiber to the home. And that will be a great revolution where a single fiber to the home can, your internet, your TV, your telephone, everything will be connected to that. So erbium doped fiber amplifiers are extensively used in fiber-based optical communication systems. EDFA was invented in 1980. Daniel DeSilver and his collaborators at 88 a revolution in fiber optic communication systems. Many people feel that they should have also had a share of the Nobel Prize. And it is the fiber optics and development of EDFAs which have made phone calls and video conferencing almost free. So I will conclude by saying, I will tell you one more thing, that the basic components of a laser are active medium and an optical resonator, which resonator provides a frequency selection and optical feedback. So if you put the active medium like the erbium doped fiber between two mirrors, and introduce a pump, you will have a laser. And the resonator makes the beam pass through and oscillate, and only certain frequencies get amplified. Those are the resonator frequencies, and this is all you know. This is the laser, and so therefore, so you all right. Let me not go through that. That's a very, you see, this is the fluorescence spectrum. This is the fluorescence spectrum. You slowly increase the 980 nanometer pump, and suddenly it starts lasing. It's one of the most beautiful experiments in physics. And an amplifier becomes a resonator, and the polished surfaces of the ends, and I have seen this myself, and in our lab, so the amplifier transforms itself into a laser. So this is what a laser consists of. You have a rare earth doped, like a erbium doped fiber, or rare earth doped fiber, neodymium, erbium, and so on. And you have mirrors at the end, and this is a fiber laser configuration. In 1961, 1 year after the discovery of the laser, Eli Snitzer took a glass fiber whose core contained neodymium ions, wrapped the fiber around a flash lamp, and when suitable optical feedback was applied, a laser was produced. That's only 1 year after the demonstration of the first ever laser, the first fiber laser. And this is another revolution that has happened. When many people feel Eli Snitzer. No, one of the greatest errors of Nobel Committee is not giving the Nobel Prize to Theodor Neumann. He has created a revolution. Theodor Neumann and Eli Snitzer, they all are in that category. And we have also facilities at RRCAT, Raja Ramanna Center. They have a big program on continuous wave fiber laser, 40 watts and many more. And you can do welding and hole drilling. Pushpa, can I have 5 more minutes? Or I should stop here? Are you there? Or?
No, sir. Sir, actually, abhi Professor Rajaram has joined नहीं किया है. If you want, you can continue for some more time. I'm trying to contact him.
All right. So you see, I will let me go through this. This is the Newton's rings experiment.
Hello.
So all of you have done this. Light reflected from this surface and light reflected from this surface produce an interference, and you see these beautiful Newton's rings. So if you have layers like this, then you can do something like this, that the thickness is such that each reflection is in phase. That will occur for one wavelength. And that wavelength is the Bragg wavelength. So this is N0 plus delta n, and this is N0 minus delta n. And the Bragg wavelength will correspond to 2 N0 lambda. Lambda is the capital lambda is the periodicity. So if you have layers of refractive indices, then they will all add up in phase for a particular wavelength. And so therefore, look at this is known as the basic principle of the fiber Bragg grating. It's a very beautiful device. You have a polychromatic light beam, white light beam, falls on a fiber Bragg grating, fiber in which you have periodic variation of refractive index. Pushpa, whenever you want me to stop, please tell me.
Sir, please continue. Sir, please continue. Please continue.
Have you been able to contact your next speaker?
Yes, sir. He's joining.
Yeah, sir. I will take them 2 minutes. So then this is the reflected spectrum. I don't have the time to go into the theory. So this bandwidth can be as small as 1 nanometer or even 0.1 nanometer. So you see, there is a photosensitivity with which you can write this grating. I will not go. So you see, you have a fiber in which you have a grating of one periodicity here, another periodicity here, another periodicity here. This reflects lambda 1, this reflects lambda 2, this reflects lambda 3. And let us suppose lambda 2 gets stretched. If it gets stretched, then the wavelength will shift. and you can find out the stretching. And so therefore, one of the very important applications of the fiber optics has been in the sensor technology. So all civil structures, bridges and tall buildings are now embedded with fiber Bragg gratings. And this Mississippi River bridge collapsed, and people say this is the collapse of the bridge. People say that if this was embedded, if could have avoided this ship by real monitoring of the health of the structure. So CGCII Kolkata have measured the temperature of this high tension cable by using fiber Bragg gratings. So this is one area, another very, very important area related to fiber optics, which has also created a vision of having very sophisticated sensors in very remote areas, and you can play around with that from a glass distance. Of course, this is another topic on which one can spend hours. So I will, and one more thing. So you see, you don't require a mirror. You write a fiber Bragg grating, and that will act as a mirror. It's a beautiful thing that you have an erbium dot fiber, and at the end you write 2 fiber Bragg gratings. So that will act as a mirror, and you have a seed laser, and which you can amplify with another erbium dot fiber. So I will skip all this, and many other experiments can be done. The references are, we wrote this book with Professor Tyagarajan, and this is my latest edition of my optics book. I have several chapters. This is a little advanced level book. This is a little lower level book for undergraduate students. Then we have a large number of books from our group. This is by Professor Anurag Sharma, Professor Vishnu Pal, Professor Shamal Bhadra. And this is again by Anurag Sharma. We developed a software. Then there is another software and experiments and so on. Thank you. Thank you, Pushpa. Thank you, Seema. Thank you, everyone.
Sir, thank you so much. It was such a nice talk, an excellent talk as usual. You are just a master. You are too good for this. Sir, yeah. But I would like to tell the audience that Professor Ghatak probably was the first scientist, first academician who started research in the field of fiber optics. So he is definitely a pioneer.
No.
Yes,
Actually,
sir. Yes, sir.
No, there is a correction there. Professor Soda asked me. So Professor Soda
yes. I know that, sir. Professor Sodha asked you, but you started the research. And the first batch of students have done their PhD with him in this area. They themselves are now so renowned, highly established academicians like Professor Tyagarajan, Professor Anurag Sharma, Professor Paul, Professor Arun Kumar, Professor Inakshi Sharma.
You are absolutely right, Dr. Pushpa Bindal. My students are much, much better than me.
No, please, sir. We can't even, we always look up to you. You are inspiration personified. Absolutely. I can vouch for that.
Yes,
so actually, nobody could have been better than him to, give this talk on fiber optics. So thank you, sir. It was really good. Very, very good. And now I think there are just 1 or 2 questions in the chat box. So may I take them?
There is a question on Cohen Tanuji paper on optical tweezers. You see, Cohen Tanuji used optical tweezers. And so therefore they use the optical tweezers of Arthur Ashkin. That's what I tried to mention. Since how can I see the YouTube questions?
Sir, there is just one question from YouTube. May I read it out to you? It is there. It is pasted in the chat box here also in the Zoom.
कैसे देखे बोल?
When I'm pasting it again, I will paste it.
हाँ, दोबारा से पेस्ट कर दो ताकि सर को दिख जाए वो वाला क्वेश्चन थोड़ा ऊपर चला गया.
ये तो सभी बंद हो गया.
Dr. Binder, you can also read this question.
सर मैं एक बार पढ़ देती हूँ. आप भी देख पाएंगे सर. थोड़ा सा अगर स्क्रॉल करेंगे अभी तो आ गया. मैं एक बार पढ़ देती हूँ. The question is by Mr. Manish Khare from YouTube.
Yeah. It is not so that the image transmission may also be considered as a form of communication. Image transmission, जैसा पहले initially it was thought, and it is still used to see the image. It is not communication. The communication is that you you pass information in the form of digital pulses. And that is how I imply the communication. अच्छा, ठीक है, बाकी सब clear है. I think
Yes,
all are
of
clear. And
course.
our next speaker is also here. So I also
No,
look
sir,
forward
you
to hear.
speak so well that everything is crystal clear. Thank you so much, sir. Thank you. And I think Prashta has Professor Rajaram joined. Can you?
Yes,
check
ma'am.
it?
Yes, ma'am.
Yes, he has
Shall I,
joined.
Yeah. Good morning, Professor Rajaram. Good morning, sir. It is certainly a pleasure to have you here. I heard your talk, the talk you gave for IAPT, and it was so good. And that is why, I kind of pursued you to give this talk because
Thank
the
you.
students will be immensely benefited. I know you're such a good speaker and you talk so well about the basics that it is absolutely, so good that
the outcome of this experiment or the message received by these fathers is really a string of 6 bits. And that's the logical way to look at it. Okay. So, whereas we multiply the W's here, it makes, if you want a model, reasonable measure of information, we should really say that we are adding the information from all these 6 locations, independent locations. And the way to convert a product into a sum, all of you know, is to take a logarithm. Okay. So this is the formula given by Shannon, right? Simplest version. So you have W, and if you had H bits of information, right? And the total number of possibilities will be 2 raised to H. That's what we just saw. So H is log of W to the base 2. Now, of course, this is very elementary, but the genius of is this. When the alternatives are not equally probable, when the different experiments are not independent, and his basic approach was to treat the process of communication as a random process. Okay, so there are at the 2 ends there is someone who's trying to send a message and someone who's trying to receive the message. Okay, and clearly, if the person already knows what the message is, then there is no need for the message to be transmitted. Therefore, to start with, there is a W or there is an H. Right? And then, when the message is actually received, this is the gain in information for the receiver. Okay. All right. Now, suppose the probabilities are not equal, 1/4 and 3/4. Okay. Then how do you do this? So Shannon gave a formula. You have to take the average of logarithm of p. Okay. So if you do that calculation, it's quite simple. You will conclude that H is about 0.8 bits. In fact, as an extreme case, right? Suppose the probabilities were 0 and 1. That means you already know what the answer is going to be, and then your information will become 0. Okay. Now, this is interesting. What it means is, if the probabilities are unequal, okay. Well, let's take an extreme case where the probabilities are 1. Then you can do something interesting. You can take this long message, which has mostly 1s and a few 0s, and you can compress the message. Instead of sending that large number of 1s, you can simply indicate which are the positions where the 0s occur. And then you would have successfully compressed the message. So Shannon's theory gave you the extent to which a message can be compressed. In fact, his paper begins with this is a different kind of apparent violation of the second law of thermodynamics. Right? The other kind, which simply depends on small numbers, we understand. It's because the second law is a statistical law. And as I said, that theme was very well developed by Einstein in his theory of the motion of small particles in a liquid, which we call Brownian motion. But this Maxwell's demon raises some interesting questions, right? Is it possible to actually send things in the opposite direction from larger entropy to smaller entropy simply by some kind of very careful, intelligent observations? Now, this question worried scientists for a while. Maxwell himself does not seem to have given an answer to this. Okay, and various people took it up in the 20th century, and there are a couple of names that I would like to mention in this context. Okay, one is a scientist called Szilard, not very well known, and if at all people have heard his name, it will be in the context of the development of the so-called hydrogen bomb. Okay, but before he worked on that, he actually said, let us take this demon seriously, but the demon cannot have supernatural powers. It has to also obey the physics. Okay, so he thought of various thought experiments. So the demon may shine some light from here to, and look at the molecule, and, measure its velocity, right? So he made it a physics problem rather than a philosophical problem. And then by careful analysis, he was able to show that, yes, you might decrease the entropy of this gas from going from here to here. But in that process, all these measurements, like sending a beam of light, and then if the beam of light gets scattered from the molecule, you have to detect it. So analyzing carefully what happens in the detector, you find that in every case, provided you do not have information to start with. If you have this information to start with, of where these molecules are, where they are moving, then of course you can reduce the entropy, right? Because you have that information, which is like a negative form of entropy, which is we have already discussed. But if you don't have that information, you will shine the torch and sometimes it won't hit the molecule, right? Then similarly, let's go to the detector. Okay. Now, detector has to be kept at a very low temperature because otherwise, sometimes the detector will show you light, which is not coming from the scattered light being scattered by the molecule, but it's just coming from the surroundings. So then the surroundings have to be very low. So then you ask what happens to the detector. In every case, Szilard and all his people who followed up realized that if you think of this Maxwell's demon as obeying known physical laws, then you are not able to really decrease the entropy. Okay. So second law of thermodynamics is preserved. Now matters remained at that point till we came to the age of computation, 1960s, right? And again, we have this very interesting connection between engineering and physics. So IBM, of course, as you know, is a company which makes, many do now, but they were the pioneers. And at IBM, there are two people, Bennett and Landauer, who gave us another interesting way of thinking about this object. They said, okay, the initial state is supposed to be random because it's a state of higher entropy, right? Then you have this demon. So the demon actually notes down which are for all the molecules, right? It has to look at the molecules on this side as well to prevent them from coming, and it has to look at the molecules on this side to allow them to come. So let us say the demon has successfully done its job. Now what happens after that? Okay, so what happens after that is that the gas has decreased, but now this demon, and of course being a modern demon, it has a computer, has a large string of ones and zeros representing the information about which molecule was going in which direction. Okay, and they argued that this string of ones and zeros in the computer also has an entropy associated with it because it's a random string, right? It's not something you can predict because the initial state of this system, this gas, was also random. Okay, so then they said, fine. So maybe entropy is not really decreased. Okay, because we have these random strings of ones and zeros. But then you can say, I can delete them. Right? I can delete the ones and zeros from my computer. So computer has come back to its original state. And now we have truly decreased it. But they made a very deeper analysis of this. And they then started to make a distinction between reversible computers and our normal computers. Okay. I'm making this. So a reversible computer is something where you have an initial state and some physical processes happen in the computer and you have a final state. And that is what you're interested in. So it has done the computation for you. Okay. But you have not expended any energy in that process, let's say. However, this computer remembers everything that it has done. Okay. So when it does the next computation, because it's reversible, all the computations that it has done in its entire lifetime are accessible to you. Okay. Now, our computers are not like that. If they were like that, if they had stored all the information which was given to those computers, all the programs from the time it was manufactured, then they would be useless. Right? So they realized that a very crucial part of computation is erasing the old information. So they looked into the process of erasing a bit of information in a computer. It's a physical process. You have a tiny piece of ferrite or some magnetic thing on a disk, and it has two possible states, and then it comes to one possible state from standard erased state. So again, this is a physical process, right? And in this process, because initially it's random, it could be 1 or 0, and then it goes to the same final state. So W has decreased from 2 to 1. And if you analyze physically how you erase, again, you find you're generating some heat somewhere. So it looks like the second law of thermodynamics and the concept of entropy, we may try to avoid it as much as we can, but ultimately it catches up with you. So both in the explanation of Maxwell's demon, in the modern concept that there is a cost even of erasing a bit from a computer, okay, we find this aspect of entropy coming out. So this is the summary of what I just told you. The first part is that the entropy is transferred to the daemon, and then it's because all the useful computers that we have are actually reversible. Okay? Because they erase information, and ultimately they give out heat to the surroundings. I'd like to conclude with a difficult question, a question which, at least to my mind, is not that very easy to answer. And this is a question which worried Boltzmann and has worried many people ever since. If you take the second law of thermodynamics and the concept of entropy very, very literally, then our world should be getting more and more disordered. Okay. So what does that mean? If you have any difference of density or difference of concentration or difference of temperature, these differences will all get equalized. And people worried about it. They even coined a term called heat death. The universe will grind to a halt. And once you reach an equilibrium state, nothing interesting happens. Right? And philosophically minded physicists also worried about this. Because you look around you, you don't see heat death. Okay. You see a system with tremendous structure and order. So, this is from a national park in Kenya. This is the famous mountain there, Kilimanjaro. It's an amazing mountain because it's exactly at the equator, but it's covered with snow, which itself tells you, right, that you have cold objects coexisting with hot objects, and you have clouds, you have life, which is an amazingly ordered phenomenon, right? And you have trees, you have grass. I mean, this is the world we live in. So when I say who ordered this, what I have in mind is how did this order really emerge? And a partial answer is given by cosmology. All right? Now, we always assume that the increase of entropy makes systems more uniform, but there is an exception to this. If you have a system where the force of gravitation is important, okay, then it can happen And in fact, there is a famous result in the dynamics of gravitating systems, which justifies what I'm saying, that above a certain size, the system increases its entropy by becoming non-uniform. So if you take an example of a star, for example, it's hot on the inside and it's cold on the outside. Higher temperature in the center and cooler temperature at the surface. And then, of course, the radiation is going into space, which is at a still lower temperature. Okay? And it's irreversible. All the radiation is flowing out. But what is the final effect on the star? Interestingly, the star is losing energy. But remember, gravitational energy is the negative quantity, right? It's a binding energy. So when it loses energy, it gets more tightly bound. So the star may shrink, right? And then the center will become even hotter. And this is actually the way stars evolve. Like our sun, billions of years from now, its center will become even hotter. Okay, it'll, instead of consuming hydrogen, it'll start consuming helium. Similarly, on a bigger scale, if you look at our current model of the universe, which is very well confirmed by observation, if you go some 13 billion years back, the universe was very uniform. There were no stars, no galaxies, no planets, nothing. Just a more or less uniform temperature, more or less uniform density. The more or less is important, not perfect. So then if you have a small increase in density, gravity ensures that surrounding matter will come and fall on that. And that is how you form galaxies, stars, planets. So the universe becomes more uniform, even though its entropy is increased. That's part of the answer. Up to the planet. Now, what happens on the planet? What happened on Earth? If you analyze, have our lunch shortly, right? I'm sure you're all waiting for it. Where did that lunch come from? Maybe from trees, maybe from animals. But where did they get it from? Ultimately, you will trace it back to the sun. Okay. Now, of course, we receive energy from the sun, but the Earth is not getting hotter and hotter. Right? Well, it is because of climate change. But otherwise, before we started polluting the atmosphere, we had a more or less constant temperature. That's because the Earth ultimately radiates the same amount of heat into space in all directions. Also, what comes from the sun is in the visible region. What is radiated is in the infrared region. So again, if you do the balance of entropy, you will find that the entropy definitely increases. Okay. Excuse me? Okay.
No, sir, please continue.
Sure.
Please continue.
Yeah. Right. So in a way, our Earth is like a heat engine. It's taking in energy at a high temperature and putting it out at a lower temperature. Okay. And converting some of that to useful work. Okay. So the plants convert sunlight into many of the things that we eat. And of course, the proteins that we eat, many of them, of course, even the proteins, the animal proteins that we eat, ultimately those animals feed on other animals, which sometimes feed on grass. So it goes back to the sun, photosynthesis, the bacteria in the roots of plants produce, the dal and protein. So in all these cases, we can see that we have a source, which, if you like, has a certain entropy. And then the net result is to increase the entropy. But in this process, we have actually created order. Okay. Now, that is the current situation. Okay. So one can sort of rationalize it, sort of explain it by saying, yes, the second law of thermodynamics is not violated. We are functioning like heat engines. And since we are not 100% efficient, we are not reversible. So if anything, we put out more entropy than we take in. Okay. Those of you who have seen that famous heat engine equation will appreciate. I could simply say Q2 by T2. T2 is greater than Q1 by T1. Okay. But actually, the mystery is deeper than that. After all, there was a time when we were not here. You had just a very hot planet, maybe with gradually oceans coming. How does life emerge? So, on the one hand, we believe in the concept of entropy. It's very well established. But we should not think that the laws of thermodynamics, the law of increasing entropy prohibits the emergence of a lot of order, a lot of structure. Right? In fact, it appears, and a lot of 20th century physics has actually gone into trying to answer this question in very simple systems. Okay, how do you get structure? So, for example, the systems which people given for a kitchen, right? You have object placed on the gas flame, liquid, right? And it's being heated from below. Now, it could have just uniformly heated up, right? But that's not what happens. What happens is you get some kind of convection happening, right? So the liquid rises, hot liquid rises, the cool liquid falls, and some kind of order develops. So this is entire development in 20th century and 21st century physics that, consistent with the laws of thermodynamics, we are still interested in various irreversible processes, which on the one hand, they increase entropy, but as a side effect, the interesting structure. So this is really a very open theme, which is being explored by biologists, explored by physicists, and explored by astronomers. So the formation of structure and the formation of order involves what we could call the flow of entropy. Okay, so entropy is more than that is generated in the system. So this this kind of is a major current theme. Okay, and many people, including many people in India, work on this theme. In fact, since you are all in Delhi, one of the people in Delhi University, a good friend of mine, Professor Sanjay Jain, I think many of you may have heard of him. When I got to know him, he had just finished his PhD and he was working in string theory. And then he joined the Indian Institute of Science. And after some time, he decided that this was a more interesting problem. So in fact, he has done some very interesting work on how you can have the emergence of order. So I'm just throwing out this hint, since he's available to you in Delhi. Hopefully the lockdown will end. You will all meet people face to face. Of course, I have to thank the lockdown because, if I had been asked to travel to Delhi at my age, I might have to Professor Seema Gupta, Professor Pushpinder. Maybe next to the coronavirus for making Zoom lectures possible. So I'd be happy to take questions on this theme. It's a very broad theme, but I hope you found it interesting.
Thank you so much, sir. It was really wonderful and informative talk. Thermal physics is also my field of interest. You explained different aspects of entropy so nicely. Shannon-Jean's theory, H is equal to log W, mathematical theory of communication, Shannon channel capacity formula, principle of increase in entropy in form of ignorance, and Maxwell's diamond, and so many things. I could not move my eyes off the screen for even a second, sir. It was a complete...
Dr. Seema, to add, this is the semester where statistical mechanics is taught in the last semester to the BSc third year students. So our third year students are learning statistical mechanics in this course, and right now they are going through this chapter of entropy and Boltzmann relation and so on. So it is the lecture has come out to be highly coincident and beneficial to the students, and in a completely different perspective. So thank you so much, sir. It was very nice.
I would add it was actually a complete understanding of the concept beyond the books. I think.
Actually, that is a sign of a great physicist, that he can bring out the physics hidden in the formula so well, so easily. I mean, what you can't see directly, he just points it out to the audience like anything. That is the beauty of it.
And the relevance of entropy in our daily life, sir. It was beautifully brought up.
It was beautiful. I would thank Dr. Pushpa Bindal that she was praising sir a lot, and now I got a chance to listen to him. It was really wonderful, sir. It was really wonderful.
But could I add a note for the students? I mean, in a popular lecture like this, one oversimplifies. So this is not a substitute for the detailed study of the textbook, solution of problems and examples, which is what will make you a more complete physicist. And I can also assure you that I went through the same process, not only in my BSc, MSc, PhD, but also in my research. But of course, now and then it's good to come back and look at the concept in a broader way and bring out the connection with the real world. So I hope that on the one hand, you liked whatever I did, but on the other hand, you will continue to become professional, serious physicists.
So it was really a wonderful talk, sir. Even in chat box, we don't have any question. I think it was so crystal clear. Everything was so beautifully explained that we don't have any question in the chat box. Because I'm not able to see any question. So
I'm seeing one.
You're able to see one, actually.
Image transmission may also be considered a form of communication. Is that the one?
Sir, that is
audio signals.
That is for fiber optics.
Fiber optics.
Okay. Oh, okay. Interestingly, I did talk about communication. Okay. But answer is yes, I'm sure.
Yes.
You can transmit anything which can be represented in bits. Okay.
Yes, we can see such good comments about your talk, and once again, we all thank you from the core of our heart. Yeah.
Yes, sir.
Okay.
Thank you so much.
Sorry for tuning in a little bit late. There's something.
No issue.
No, sir. You were well in time.
Issue. You're well in time.
You were well in time. Thank you so much.
Thank you so much, sir. Thank you so much.
So with this, we are completely.
Link is shared.
Yeah, I
with
will.
the participants.
Okay. Yeah, the feedback link is shared through the registered email ID. So you kindly fill that form because it is open only for a few minutes. So it has been mailed to you. So and please, Dr. Seema, please announce.
Yeah. So with this, we are completed with the first half of presentations from eminent speakers. So as Dr. Bindal told you that we have provided feedback forms on your mail. So please fill it. It will be open only for 10 minutes. And it is also required for your certificate. So please fill it. So now we take a break for lunch. We request all of you to join back sharp at 2 p.m. for the next set of presentations from Professor Anurag Sharma and Professor Vijay Singh.
Yeah, please look forward to those talks because they are again going to talk about very basic concepts and you are going to study these in your curriculum. So do come back on time and you can definitely look forward to these talks.
Yeah. So let's meet at 2 p.m. sharp.
Yeah. Okay.
Bye then. Enjoy your lunch.
lecture. So what I have chosen is I am going to talk about the the concepts in optics which are purely theoretical, in the sense the ones which came out of the mind of this thinker. So what are the basic things that we have in optics? Of course, you start with rays when you talk about geometric optics. Then the waves were developed. Then the waves were identified as electromagnetic waves, and finally came the photons. And each of this, these happened at different times. Rays were known for time immemorial, from Greek times and so on. Waves were first postulated in 1678, and EM waves in 1865, and photons in 1905. And what are the principles that I'm going to talk about? Fermat's principle, Huygens principle, which is Huygens-Fresnel principle, Maxwell's equations, and photon and the stimulated emission. So what is common in all these 4 topics that I have chosen? They are all products of the thought process, and they show the brilliance of the thinker. They have stood the test of time and are valid even today. Each one has been responsible for initiating a new era in the field of optics. So let's first look at, put this out of the way, sorry. I'm seeing some screen in just a minute. Okay, let it be. Okay, yeah. So Fermat's principle. I'm sure you have studied Fermat's principle in your college somewhere or the other. The original statement of Fermat's principle was the actual path between 2 points taken by a ray of light is the one which takes the least amount of time. What does it mean? It means if you have point A and point B, and the light has to travel from here, and there are several paths, this black line and this red dashed line and the blue dashed line, these are all nearby paths. That's very important. They are all nearby paths, possible path the light could have taken. Then the light will take the one which is the smallest in time, which takes the least amount of time. So if I look at the same thing, let the time taken from A to B be TAB, and the time taken along the path 1 is minimum in this case, then that is the actual path. So if I really draw this time as a function of paths, I have written here path 1, path 2, path 3, but there can be some parameter which will decide these paths, and then that parameter will be in the x-axis. But here it is just notionally. So you see the time taken is minimum for path 1. So that is the actual path the light will take. It will not take this path or this path, because time is continuously decreasing if you go nearby paths. There's no minimum here, right? So what does it mean? Here, then 1 upon c will come out, and that will vanish because of the 0 on that side. It means that the optical path, which is called, this integral n ds is the optical path. The optical path from A to B must be minimum. That is the Fermat's principle in the original form. So it is the optical path length is the shortest along the actual path. Later on, it was realized that this is not the complete statement, and hence the correct statement was that the actual path between 2 points taken by a ray of light is the one for which the optical path is stationary with respect to small variations in the path, which is the same statement as this. This equal to 0 is not only for minimum, but also for maximum and also for stationary. What does it mean? If the paths are such that the path 1 is minimum, then that is the actual path, or it could be a maximum, then also that could be the actual path, or it is stationary. What does it mean? If there is a path, if you change on either side by a small variation, then there's no change. Then that path is also a valid path. So these are the 3 situations which occur in Fermat's principle. Path could be minimum, it could be a maximum, and it could be a stationary path. Stationary is like actually a point of inflection in mathematics. As we say, the curvature goes through a change. Here it is a one sign of curvature, here is another, and at this point it is actually changeover. So even the curvature is 0. Okay, so the minimum path is very common. In fact, in uniform space between 2 points A and B, the straight line is the shortest path. So that is why in uniform space or uniform medium, the light travels a straight line, which is well known. But what are the examples of other paths which are often not given so clearly in the books? So I thought I have created one example where all these will come together. So let's consider a reflecting ellipse. So this is an ellipse which is reflecting from inside. And let us consider A and B are the foci of the ellipse. This is focus 1, this is focus 2. And we know that in an ellipse, by definition, this length plus this length is always same, where this point. These paths are, all these lines are equal. So if there's a uniform medium inside this ellipse, then light ray from here, suppose there's a point source at A, the light will go, get reflected and go to reach B. Okay? And similarly, this will also reach B. And if I take a nearby path, will also have the same length. And that means each of these paths is actually a stationary path because nearby paths also have the same length. So if I want to plot, let us say, I consider the definition of this point, but this angle theta. So at theta equal to 0 is this point, theta equal to positive values up to 90 are as you move here, and theta negative goes like this. So if I plot the optical path length from A to B after one single reflection, as a function of theta, it will come out to be a straight line. What does it mean? That means if I take any point on this, it is a stationary point because nearby points also have the same value. So all of them are stationary. So all the rays from point A after reflection will reach point B because they have all the, and this property we know in other context also, that if you have a point source here, the perfect image will be formed at B and so on. Now, let us now construct an ellipse whose major axis is the same, but minor axis is now slightly larger. This red ellipse. Okay, we have sort of kind of inflated the ellipse here. Now what happens? Now this A and B are no longer foci of this red ellipse. They were the foci of this. So they are two arbitrary points which are symmetrically placed around the center. This is just an example. Now, let us look at this yellow path which is going, that means A, P, and B. Okay, A, P, B is of course larger than A, small p and b, and A, small p and b is the original ellipse. So that is a particular path. So the A, small p, b, or A, small q, b, or A, small s, b, they're all equal. They're all equal. But in this case, since A and B are not foci of this red ellipse, they're not all equal. But you can see from here that this A, capital P, B is larger than A, small p, b. Similarly, A, S, B is larger than A, small s, b, and A, Q, capital Q, B is also larger than this. But as I move in this direction, this difference becomes smaller and smaller. So this path here, path going through P and small p, so the path is difference is much larger than the difference here. And ultimately, when it comes to point P, that means the ray which is coming from A to R and getting reflected to go to B will have the same length as earlier. So what does it mean? It means that the path from here, if I now plot as a function of theta, the path will take this thing. At 0 angle, which is at P, it is a maximum. Then it goes down. At Q, it passes through at this thing, and then comes to a R where it is minimum. And if I go down further, then it will again increase. On the other side also, it will start from P, go to S, go through S, go to T, which is again a minimum. Now, so what are the rays possible for this red ellipse now? The rays possible are P is a maximum, R and T are minimum. That means this ray is a valid ray. And this ray which goes to R and comes to B, and this ray which from A to T and comes to B, these are valid rays. All this S and Q rays are not valid because they are not going through a maximum or minimum. They are just going through a monotonic change here. Okay, so in this ellipse, you will find that this is an example of a maximum path, because on either side, the path decreases. And this is an example of a minimum path, because on either side, the path increases. If I take a point here, this particular path is larger than this. So on either side, it increases. So this example actually gives you all the three cases together. With the black ellipse, you have the stationary condition. With the red ellipse, you have maximum and minimum condition. So that is a third example which I can give here. So Fermat's principle is consistent with Snell's law, which was established experimentally. And that is the success of the principle. Because principle, when you enunciate, there's no, this is just a principle that you have stated. But it sort of governs all the laws of all the cases which the Snell's law actually shows experimentally. In some cases, Fermat's principle gives results very easily. For example, the focusing in an elliptical mirror, as we just saw, or a parabolic mirror. It is very easy to show that a parallel ray of light from a parabolic mirror will focus to its focus. Whereas doing it through a Snell's law would require more complicated algebra. It has led to the principle of least action in mechanics. Of course, Fermat's principle was the first one of this kind, and then it further led to other least action principles. And in mechanics, we have principle of least action. Okay. So the light propagation, let's look at how far we have reached. The Fermat's principle gave the clue, or gives the clue about the path the light takes from one point to another. But how light propagates remains still a mystery. At that time, the corpuscular theory of light propagation, which was started by Descartes in 1637 and expounded by Newton to a great length in 1672, was in vogue. And Newton was a big man. It was difficult to oppose him also. So a lot of people actually believed in that particular theory of corpuscles. However, it could not explain many experimental results. For example, diffraction, it could not, and many other. But still, people sort of understood. In fact, I don't know whether you know that the famous Newton's ring were never observed by Newton. They were observed by Hooke experimentally. Newton only explained them on the basis of his corpuscular theory, and that was also wrongly. But somehow they are now known as Newton's rings. Okay, Newton's role is actually negative in those. So now, the next step in the how light propagates was given by Huygens. And Huygens' principle is again a purely theoretical thought by Huygens, and he proposed in 1678 the wave theory of light. It's not exactly a wave theory, but wavefront theory, I would say, of light. And he introduced the concept of wavefront and its propagation. And what he said, that if this is a wavefront at a given particular time and position, then each point, and I have shown only a few points, but continuously every point on this wavefront will act as a source of a spherical wave, which I have shown here, for this I have shown here, and so on, and a common tangent. And after a certain time, all of them will reach at a certain point by the velocity of light, and a common tangent to all these will represent the wavefront after that time. And this is what is, so these are known as secondary wavelets. This is the primary wave. This is known as the secondary wavelet. And from this wavelet, you can, of course, if this is a spherical point, this will be a spherical wavefront. But when you make a common tangent, then this will touch this wavefront at one point, and that is the common tangent that becomes. This was the Huygens hypothesis, and which became a principle after his success, because it was successfully, it could explain refraction, it could explain rectilinear propagation, and many other things. And so it became a principle, Huygens principle. One problem with Huygens hypothesis of secondary wavelets is that the being spherical waves from a point, the secondary wavelets being spherical waves from a point, will also propagate in the backward direction. If this is a point source, it will give you a full sphere. And so if you want to make a tangent here, there will be a tangent here, but you can also make a tangent on the other side. And hence, this would result in also a wave going backward, which was not really true. Wave is going only in a particular direction. Huygens ignored the backward waves without any justification. The principle could explain propagation of, as I said earlier, plane waves, spherical waves, refraction, refraction, and could not, however, explain diffraction. There was no, today, of course, we use Huygens principle to study diffraction, but actually, it is not really, Huygens did not could not explain diffraction on the basis of his principle. And that was done by Fresnel. Fresnel in 1888 used Huygens' principle and the ideas of interference, which were already established by then by Thomas Young in 1803. So now you had the Huygens principle. You also had the concept of interference, basically concept of superposition. And he based his theory on these two things. What he proposed, that all these secondary waves which are coming from, what Huygens had done, he had taken one secondary wave at a time and taken a common tangent. What Fresnel said, that if I'm trying to find the field at point P, the light disturbance at point P, then all these secondary wavelets which are coming from all these points will contribute to this, and they will all add in phase with their own phases. So this has traveled more than this, will have a different phase, and they will all go. And so they will all wave superpose and they will interfere. That means they will add in, superpose in along with their amplitude and phase, and to give the final amplitude here. So this was the theory given by Fresnel. Fresnel also extensively studied polarization and put forward the hypothesis of transverse nature of light. So the first time anybody who had said that the light is transverse was given by Fresnel. Okay, it's largely transverse. I mean, not exactly transverse always, but it can never be just longitudinal. That means if a wave is going in the z direction, you can have electric field in the z direction, but you'll have largely in the transverse direction. But you can never have an electromagnetic wave which has only Ez if it is propagated in z direction. That is largely the meaning of being transverse. In sound waves, you could have waves which were actually longitudinal, but not here. And that is so with that, he said that if you want to explain polarization, then you must assume the light will be transverse. So his understanding of these waves led him to introduce the obliquity factor, because, in polarization, it was known that if you change the angle, the effect of polarization would be different and so on. So he could see that there's an angular dependence of light luminance. And so he introduced obliquity factors. So what he said, at this point P, the field from a particular wavelet would be given by A, the amplitude of the primary wave, I by lambda, I'll just come to that, e to the power minus IKR by R is the spherical wave factor, and chi of theta, which is the obliquity factor. And chi of theta, what he gave was 1 by 2, 1 plus cos theta. So when theta is 0, this factor is 1. When theta is 180, this backward direction, this factor is 0. At 90 degrees, this factor is smaller, which is 1. This I by lambda was also introduced by him to satisfy the conditions of known results. And this also gave that the secondary wavelet scales in amplitude as 1 by lambda, and also has a phase difference with the primary wave, which is of pi by 2, because I is nothing but e to the power I pi by 2. So that means the light, which is kind of scattered light in some sense, is also out of phase with respect to this, in quadrature phase actually. Now this provided a mechanism for suppression of backward waves, because then in this direction there was no wave. He introduced this factor, of course, ad hoc manner. It's the same argument we have read earlier. Einstein also showed in this process itself that the light photons that interact with the collection of atoms or molecules, either through emission or absorption, must be of the frequency nu, such that the photon energy h nu is E2 minus E1. So it should exactly match, only then it will interact. And the light interacts with matter as photons of energy h nu. Finally, the photon that is emitted during the stimulated or induced emission is identical in frequency, phase, polarization, and direction as the incident photon. This is really a remarkable consequence and has been responsible for the coherence properties of laser beams. But for this, the lasers which are coming out will not be coherent. So although there were some confirmatory works earlier on the stimulated emission, the experimental proof came in 1954 when Towns and Shallow invented MEASURE based on this particular phenomenon. MEASURE is a microwave amplification through stimulated emission of radiation. Subsequently, the first ruby laser was invented on May 16, 1960, as Professor Ghatak said in the morning. May 16 is why it's called the Day of Light by Mayman. So what happens in a laser? So you have a collection of atoms in which one photon comes and there's a stimulated emission. So you have excited. So basically what is required if you want to dominate stimulated emission over induced absorption, the number of atoms in the upper level should be more than the lower one. That is known as the condition of population inversion. So for a laser, that is necessary. Otherwise, this photon will have more probability of getting absorbed than leading to a induced emission or stimulated emission. So, but let us say you have more atoms here. So this photon will create two photons. Then there are two mirrors on the side to make a cavity. So these two are reflected back, and then when they come through again, they become 4. Then they come back, they become 8 and 16 and so on. And within no time, they become millions. And this mirror, one of the mirrors is kept as 100%. The other mirror is kept less than 100%. So the part of the beam comes out as a laser beam. That is the output you have. So usually the energy that inside the intensity of the beam that you have, which is coming out, is only a small fraction of the intensity that is inside the laser. It's because this is usually 95% or 99% or 98%. The cavity, as Professor Ghatak had mentioned, but we will not go into the details. He also could not have time to go. Cavity also is responsible for making the line refined. In the sense, the monochromaticity of the laser beam is actually responsible, is due to the this particular cavity or resonator. So lasers have really revolutionized optics, and some of the examples were given by Professor Ghatak in the morning. In fact, in order to encompass the vast new areas developed and numerous applications, the new word photonics had to be coined in post-60s. Lasers are now ubiquitous in everyday life, from laser scanners to oximeters. I don't know, the oximeters that you have on your finger to fight or to monitor your COVID kind of things is actually a laser device. If you see inside, there's a laser. The 120 years of history, and Professor Ghatak also, talked about some Nobel Prizes in his talk, and I give you some statistics here. In the 120 years history of Nobel Prize, they started in 1901, and today we are 2021, is neatly divided by the lasers in the middle at 1960. So you have pre-laser era, which is 60 years, and post-lasers, another 60 years. So the pre-laser era of 60 years, the full Nobel Prizes are given to optics. In the post-laser 60 years, 14 Nobel Prizes have been given to the optics and photonics. So you can see the jump after lasers. So lasers have really revolutionized thing, and this is all started with the thought process of one person called Einstein. The photonics industry is expected to grow at the 8% annually in the next 5 years. However, in our country, we are just waking up. Okay? Thank you very much. Wake up.
Sir, we are wide awake. Don't worry.
No, I'm talking about with respect to the optics.
The whole optics is revised, sir. The whole optics is revised. In such a easy manner.
Thank you so much. Thank you for such an excellent talk. You took us all on a journey of Fermat's principles, Snell's laws, and all theories of light, corpuscular, then wave theory, and then Maxwell, basically electromagnetic theory, and also a bit of wave particle duality. And you also made us understand the concept of lasers once again so beautifully. So thank you so much. It was really very, very good. And Let me see if there are any questions on the chat box.
No, ma'am, no questions are there.
Oh, everything was so crystal clear.
Yes,
So,
ma'am.
Yes, it was
That's
so
a
well
standard thing.
explained, sir. It was so nice.
yes, sir, very nice. Indeed, an excellent talk, and we are really
Yes, sir.
thankful. Therefore, you specially
When there's
prepared
no
this.
response, when there
Covered by Virahank, and this was the golden ratio, also hinted at by Virahank. Then what happened? Then what happened is the following. We have some interesting history now. Okay, history of mathematics, you might say. Indian mathematics traveled with the Indian spices along the spice silk route. Okay, so it traveled, and you can just imagine yourself, put yourself back 1500 years ago. Just as the spices traveled, the mathematics also traveled on camels and caravans south of the Caspian Sea, north Persia, down to the Mediterranean, and then it entered Europe via Istanbul, and the first country it entered into was Italy. Not very surprising, Italy was the depositor. It got not only our spices, and you had a lot of rich merchants, including the Merchant of Venice, Shakespeare, but it also, the first universities were set up there. It was basically a transfer of knowledge from India and China to Europe. So similarly, our Virahanka series also traveled that way. It traveled from India to Italy. Okay. And there was one mathematician there who was very enamored of this, okay, who liked this series a great deal, and his name was Fibonacci. Okay. And I have not mentioned him here, but then he said I can generate the series also by another method, by a rule of rabbits, he said. Okay. Now Fibonacci was the Italian mathematician who liked this number. Okay, it's also, by the way, now known as the Fibonacci series. It should be, strictly speaking, the Virahanka series. He says, consider the rule, there is a mother rabbit which gives birth to one daughter rabbit every year. Okay. There is a daughter rabbit which grows up in 1 year to become a mother rabbit. And the third rule is that rabbits are immortal. Okay. With this rule, he said, I can generate Virahanka series. Okay. And how does he do it? Let me show it to you. First year, you have only the mother rabbit. Second year, you have the mother and her daughter. The third year, the mother gives birth to another daughter, but the daughter grows up to be a mother, so that is 3. The third year, the year after that, the mother gives birth to a daughter. You can see these two. The daughter grows up to become a mother, and this mother rabbit gives birth to another daughter. So again, you get 1 of 3 plus 3, and then 5, and then 8. And in this fashion, you have what is known as Fibonacci rabbits. And you get the golden ratio. So that's the golden ratio. It's an interesting series. I have to tell you something about Fibonacci. Fibonacci not only got this number popularized in the West, okay, but he did something interesting. He got the European mathematicians to accept the number 0. Prior to that, the number 0 or nothingness was banished because it was the sign of the devil. There is no such place as 0. There is always God there, they said. Okay. What Fibonacci convinced them, the mathematicians, that forget about doing mathematics. You can't even do trade with the Arabs and the Indians if you don't accept the number 0. So let me continue with my story. The story goes on, and there are other representations of this number now. It is basically the solution to the quadratic equation, x squared minus x minus 1 equal to 0. Okay. So you basically, when you solve this, we all know the solution at 9th standard level, 1 plus root 5 by 2, you get the Fibonacci number, or you get the golden ratio, 1.618. Why golden? We'll come to it in a minute. Okay. The other solution to it is minus 0.618. And very interestingly, if you multiply these two solutions, you get minus 1. Okay. So that's another mathematical representation. But there is an even more interesting one inspired by Ramanujam, okay, in terms of continued fractions. What Ramanujam would say is that you take x equal to 1 plus 1 and you divide it infinitely continued fraction wise all the way down. And since, as we have a Sanskrit saying, Om Purnamada Purnamidam, the infinite is contained in the infinite. In the denominator over here, which I'm now circling here, let me highlight this. In this denominator over here, you replace it by x. And if you replace the entire denominator by x, you will get this quadratic equation x square minus x minus 1. So about Ramanujan, it is said that every number was a friend of Ramanujan, or vice versa. Ramanujan was a friend to every number. Every number he had something special to say. So what I hope that is by the end of this talk, you will become friends with at least one number, and that is the golden ratio. 1.618 dot 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 dot. Okay. So that is about some medieval mathematics. Let us continue. Okay. What is got this? Why is this called golden? What is this got to do with ratio? It is basically a question of proportion. Okay. So you have to see the slide in a somewhat convoluted way. If you look at the top left, this is the Parthenon in Greece, okay, near Athens. Okay. What they say is that if you look at the breadth, okay, and you look at this height, and you divide the breadth by this height, you will get the golden ratio. It's like 1.62. Leonardo da Vinci, the great Renaissance person, was also very enamored with this ratio, golden ratio. Okay, he said that if you look at Mona Lisa's painting, they say the distance between the 2 ears, okay, you put it in the denominator, the distance from the height to the chin, you put it in the numerator, and that ratio is also 1.62. It's a perfectly proportioned figure and face. Okay. Not only that, he drew what is called, and which is probably not very clear in the slide, something called the perfect man. It's called a Vitruvian man. It is based on an idea due to Vitruvius. What Vitruvius said is that any structure, including a human structure, should have three things. It should have strength, it should have functionality, okay, and it should have beauty and proportion. And he said the proportion should be in the ratio of the golden ratio. For example, if you stretch your arms wide, and if you look at the height divided by the distance between the stretched arms should be 1.618 or 1.62. Once this was discovered and this was made popular, okay, and by the way, it has been made very popular by Dan Brown in his book, in all the series of books that he has brought out, okay, the golden ratio phi, as he calls it. The Indians also discovered it. For example, people say that the entrance to the Taj Mahal is as per the golden ratio, okay. But then I found something interesting about 7 years ago when I was traveling near my village. I went to a wedding place, and particularly among the folks in Bihar, that wedding room, so to say, where the bridegroom and the bride have to spend a few nights and a few days together. Okay, the wedding room has a wall which is painted, and on that painting, I saw a painting which you are seeing, which I have now, which my cursor is at right now. There was a big circle, and inside that there was a dark circle. So, taking a scale from the local schoolboy in that house, I measured the ratio, and the ratio turned out to be 1.6. Okay. So this turns out quite interestingly. I thought it was the golden ratio. At that time, Dan Brown had made the golden ratio very popular again. Okay. And if you look at for example, this painting of Shiva, and if you look at the moon is as per the golden ratio. Okay. Let us continue with the element of beauty for the moment. Okay. What I'm trying to say is, according to Leonardo and many other architects, the best proportion is one which is 1:1.618. Okay. If you have something like this, it looks very thin. If you have something like this, it doesn't look good, but this proportion looks proper according to them. Okay, so which rectangle do you like the best? I want the universal answer, like the middle one. Okay. But there is something else. The story doesn't end. The mathematical story continues, and I will come back to the mathematics in the end. But let me alert you to something right now. Okay. I will first look at the square. There's a square with unit size 1, another square next to it with unit size 1, and then there's a bigger square which is 1 plus 1, which is 2. And then 2 plus 1 is 3, a third square, 3 plus 2, 5, a fourth square, and 5 plus 3, there's another square, which is 8. Okay? Right? So you have this. Now you do one thing very interesting. You start from one vertex of the smallest square, and you draw a curve which is a tangent to it, making sure that it hits the boundary between the two squares 1 and 1 as a tangent, and the boundary between 1 and 2 as a tangent, as you can see, the boundary between 2 and 3 as a tangent, 3 to 5 as a tangent, and 5 to 8 as a tangent. Okay, so you draw this curve, which is a spiral. It is called a golden spiral. Okay, it is a curve which is also known as the Fibonacci spiral, and it was made very popular by a later mathematician, Bernoulli, who was very enamored of it. Okay, and he liked this curve a lot, so that he has got this curve plotted and sort of engraved on his grave, actually. Okay, so there's one thing very special about this curve, which I should just point out to you, and that is if you go to the center of this square, of the spiral, sorry, not the square, of the spiral, and you draw any line to the curve, okay, and at this point you draw a tangent. The angle made by a tangent at any point and the line joining that tangent point to the center of the spiral will always remain constant, will make a constant angle. For example, if I draw a tangent at this point, you can see it, you may not see it, but let me draw my cursor like this, and you draw this point and connect it to the center of the spiral. Say the angle is 60 degrees. If you take any other point, draw the tangent at this point, and then join that tangent point to the center, that angle will also be 60 degrees. Okay. So what it means essentially is that as you go around this curve, you must make only a constant angle of 60 degrees to watch the center of the spiral. Okay. Now, this golden spiral is there. People, as it is, people discover things which are not there. You try to see things which are not there. So people started saying golden spiral is everywhere. Okay. Whether you look at a conch shell, you look at a rose flower, you look at the sunflower, or you look at the spiral galaxy, you will see golden spirals. Not so, I would say. But anyway, you can imagine that this is very popular and this is true. So let us say the golden spiral is everywhere. Okay. Right. Okay. Then the question arises is, you have told me the following. You have told me the mathematics. Then you have told me why the golden ratio is so popular in Western aesthetics and sense of proportion. What about physics? Okay. So before I launch into the physics part, I'm still in the first, I would say, trimester of this talk, so to say, first 1/3 of the talk. If you go to the physics part, but let me pause for a minute. Is my voice audible and clear?
Yes, sir.
Yes, sir.
It's clear.
Yes, sir.
Thank you very much. Okay.
Yes, sir.
Thank you very much. So I would like, okay, so let me show you one and then I'll go back to the previous one. Here, in physics, for example, you see these problems. For example, there's a problem in the European Journal of Physics in which you have infinite capacitors. Okay, equal capacitors, but they go on infinitely. And you say, what is going to be the effective capacitance of this network of capacitors? If you work this out, it turns out that it's going to be C0 into the golden ratio, 1.618. Okay. Additionally, and how does it happen? I'll tell you how it happens. Okay. And that's why I have to go back now and show you this curve. You take infinite series of resistors. Okay. Take the infinite series of resistors and you say, what is the effective resistors between these 2 points? I have not shown you that infinite series, by the way. That's why I showed you the infinite capacitors, to get you an idea, get you a feeling for what I mean. What you do is you truncate that series and you replace this infinite series by itself. The same idea as how the infinite is contained in the infinite, part of what is there in the Upanishads. Om Purnamada Purnamidam Purnata Purnamudachyate. Okay. You put that in here. Okay. And now you say, what is going to be the resistor, effective resistor here? It is very simple. This is equal to R. Okay. I've got an R over here. Plus these two are in parallel to each other. So you'll get R equivalent into R divided by R plus R equivalent. It's written right here. Okay. And if you simplify this, you'll get a quadratic equation. Okay. So what I'm saying is that if you do this, if infinite resistor network properly, you'll get a quadratic equation of this type. And if you divide this entire quadratic equation by R square, okay, that is, you say X is equal to R equivalent by R, I get the same equation which leads to the golden ratio. So the answer is the equivalent resistance is equal to R into the golden ratio. Okay. So that's where you see it. It's a work by T.P. Srinivasan in the American Journal of Physics long ago, 1992. It's also an IIT problem, by the way. It has come in IIT already. Okay, and it is basically uses this idea that the infinite is contained in the infinite. So in capacitance, you see. Then there are some scattered problems in which you can see. There are one-dimensional toy models where you can see it. Okay, but these are all scattered occurrences. Okay, this golden ratio phi is the golden ratio phi. I'm getting a disturbance here. Saroj, please.
Please mute yourself.
I'm so sorry. No, there's a kid who is disturbing me. Okay. Happens to be my grandson, who doesn't realize that I'm giving a very important talk.
Sorry. I thought some
no. He just barged in. I don't know.
Really sorry, sir.
No, I'm sorry. Because anyway, that was a good diversion. It is not like pi or e. When you look at pi, it is such an important irrational number. Okay, that it occurs everywhere. Time period of a pendulum. If you have Kepler's third law, t square proportional to r cube, again there it appears pi will come. If you look at, for example, the Bohr quantization rule, the Bohr-Sommerfeld quantization conditions, h by 2 pi, this pi is everywhere. It is ubiquitous. So is E, the base of the Naperian log. You look at the growth of bacteria, you look at the decay, nuclear decay, you'll find the C. The golden ratio is not like this. Okay? It comes in scattered ways, it will come, it will not come. So what I'm going to tell you now, okay, in the next 20 minutes or 30 minutes, and I've already, I think it's been about some time now, what I will tell you is basically that we have found a universal occurrence of the golden ratio in physics. Okay, that's the lesson. Okay, so let's continue. So we go to the third theme of the talk. I've told you a little bit about the mathematics. I've told you about beauty. I've told you how golden ratio is never found anywhere in physics or very rarely found. It is not as popular as Doyen Brown would like you to believe. Okay. By the way, I will tell you a little bit more about this Dan Brown later on. Okay. We come to the center of mass, the third theme. That is how I tie it together. You can find the center of mass in a number of ways. Okay. The simplest way is what you see on the right-hand side. It's called the knife edge method. Find the point at which you can separate, at which you can support a laminar body, and that is the golden ratio. You have a pen. I think you're all carrying a pen, and if there's a desk, you want to know what is the center of mass of your pen. All that you'll do is you put the pen on the table and you will slide it perpendicularly along the edge of the table and see where it falls. And that is the point of the center of mass. Okay? So that is how it is found. Center of mass, I have to tell you, is like a very important concept in physics. Okay? And we all know about it. I mean, and it's also very useful in life. For example, if you look at this, the center of mass of the human body, here is the knife edge method. There's a yogasana which tells you what is the center of mass of the human body. It is very close to the navel. This person at the beach is doing Mayurasana. The center of mass was used in a very, very intelligent way and a wonderful way by a person who did revolutionized high jump. Okay. It's called the Fosbury flop. Prior to Fosbury 1966, 68, I think, 68 Olympics, everybody would jump a high jump bar in the forward direction, like a horse jumping over. What Fosbury did was he jumped backwards. Okay. And he created a sensation because he could jump at least half a feet higher. What he is doing essentially, as you can see in this figure, is he's keeping the center of mass as low as possible. Okay. Half his body is below the bar, half his body is above the bar. His center of mass is just above the bar. And he has cleared it. If you jump in the forward direction, your center of mass is at least a foot above the bar, if not the entire 2 feet above the bar. Okay. And this is called the Fosbury flop. There is a physicist. He's done his BSc in physics. He's the greatest hurdlist of all time. His name is Edwin Moses. He did the same thing. He calculated the distance between two hurdles, measured his steps in such a way, and he ran in such a way that he always kept his center of mass as low as possible as he's jumping over. Okay. He's won the largest number of gold medals as far as the hurdles go. And he's Edwin Moses, a BSc in physics. So he's used this physics to advantage. Okay. After he did it, you can see everybody and his brother and sister started jumping in the same way. Okay, this jump, jump, jump all the time. The center of mass is intuitively obvious to this kid on the beach, as he's balancing himself or herself. I don't know if it's a boy or a girl. Okay, and this is here what you follow the Bombay Darshan bus. A wrong use of the center of mass. All the kids are on top. I mean, the bus is top heavy. It's about to fall. If you ever go to Bombay, don't board this bus because it's likely to fall, and don't go near it because it might fall on you. Okay. So it's a very useful concept. It has been used also in what is called the wobble method. Let me not, this is too elementary. It is a very heavy boy. There's a lighter girl. The heavier boy has to be close to the center of mass to balance this plank. Used where? Used in actually finding out extrasolar planets. Because you have the planet and you have the sun or the star and you are watching it. What happens? As the planet goes around, okay, the star wobbles, it goes back and forth so that the center of mass, which is shown by a red cross, is fixed. So the planet is going around, the star is wobbling. You never see the planet. When you see extrasolar planets by a telescope, or the Kepler telescope or whatever, you never see the planet, you see this wobbling. And you never see the wobbling, you see the Doppler shift. Okay, but the concept is very simple. The concept is the center of mass and the invariance of the center of mass as two bodies move. So the idea is all these things are important. Okay, the maths is important. There's a golden ratio, 1. Okay, and what is also important, can you also see me or you cannot see me? Should I, is my camera off or something?
Sir, your camera, sir, you are not visible.
No, you are not visible.
But your presentation is visible.
Good, as long as it is, the face is not important. Okay, but sometimes the gestures are important. Okay, so this is the one thing I don't like about online. Okay, because I can always never get the technology right, I find. Anyway, so you have the golden ratio, mathematics, you have some talk on diversion on beauty, and you are now told about the center of mass. So now let me put it all together, okay, in the next 15 minutes and tell you the story, okay. Oh, by the way, there's more on the center of mass. I mean, the center of mass, by the way, leads to bilateral symmetry on Earth. If you have one wing on this side, you have another wing on the other side. This leaf has to have bilateral symmetry because if one side is heavier, it will sag. So if you have one hand, you have another hand. If you have one leg, you have another leg. You have to be symmetric. You must have bilateral symmetry demanded by keeping the center of mass at the center. Okay. Same thing with this beautiful peacock, okay? It has to keep the center of mass at the center. Same thing with the ballet dancer. She may be dancing and she looks very pretty as she dances, okay? But the center of mass is right here at the foot. It goes straight through. Okay. So the center of mass is also, as I said, not just a useful concept, it's a beautiful concept, okay? So just as Vitruvius said, that any structure must have strength, functionality, and beauty, center of mass has not only importance of its own, but it is also beautiful. Okay. So now how do you calculate the center of mass? Actually quite simple, okay. All that you do is you sit over here, if this is the origin, you just take m1 into whatever the distance is, in this case, the 2 kg mass is at 1 meter. If the 4 kg mass is at 4 meters, then you divide it by the two masses, you'll get 3. Okay. I'll pause at this to tell you that there is another way to find the center of mass, which all students at 11th and 12th level should know, or probably do know. Okay, and that is the following. You sit at the center of mass and call it the origin. Okay, and you know the distance between the two masses. It is 3, 4, and this is 1. 4 minus 1 is 3. You sit over here and you say, okay, let this distance be x. I don't know what it is, but let it be x. I know the total distance, but I don't know where my center of mass is. I sit here, I do 1 x into 4. 4 into x is equal to 2 into 3 minus x. And if you solve this equation, again, you will get x is equal to 1 centimeter or 1 meter which means this is 1 meter from here. Okay. So the second way of doing it tells you don't have to do any denominator calculations at all. You just sit at the center of mass, set xcm equal to 0, and just do 4 into x is equal to or minus 2 into 3 minus x is equal to 0. Okay. So that's the faster way of doing the center of mass calculation. Okay. So now our story begins. Okay. And let me start with it. The story actually began in 2014. Some of you are familiar with the Kishore Vaigyanik Protsahan Yojana. Okay, it's a very important scholarship exam of the government of India. Okay, and at least 1 or 2 lakh students sit in it now. Okay, this was 2014. This was a question that Dr. Praveen Pathak and I had set. We asked the very simple question that here you have a square. The square has a side A, therefore it has an area A square, and therefore its diagonal is square root of 2A. I remove a smaller square from here. From the vertex, I cut another smaller square, and I ask the following question. How much of the square should I cut so that the center of mass will be at the edge G? Okay. If I cut only a very little amount of the square, a smaller square here, then the center of mass is well within the bigger square. If I cut more, then the center of mass is outside it. Okay. But if I cut just the right amount, I will get a golden point, and that point is the center of mass is right at G. Okay. And what should this ratio A by B should be so that I get it right there? Okay. So now I think you know the answer. It will turn out to be the golden ratio. Okay. But let me go through it a little bit. Okay. This is the same problem, the same thing. And here is the calculation. Okay. In this calculation, all that I will request you to do, I will go over this calculation twice for you, and then I won't go over the more complicated calculations. But I think I should do this at least so that you will know how to do it tonight if you're at home and you want to amuse yourself. Okay. You look at the mass of the square, the total square. The mass of the total square is m0. That I write as rho into a square. Rho is just the surface density or the superficial density of this laminar body, the square. Okay. You look at x0. X0 is the position of the center of mass. Okay. And if you're sitting here at the so-called mythical center of mass, okay, this x0 is nothing but GB minus GO. That is what is written here. GB minus OB, sorry. Okay. GB minus OB because the center of mass is just GO. Okay. Right. So what is GB? Not difficult. GB is just root 2 into B. So I'll go down here. GB is equal to root 2 into B. And what is OB? OB is this thing. I just point out. This is OB is equal to root 2A divided by 2. So it's A by root 2. Okay. Minus, because I'm subtracting and cutting this out, minus the mass of the smaller lamina, which is rho into B square. Okay. That is the rho. What is rho? Rho is the density, superficial density, and B square is the area of this so-called lamina that I've cut out into G times O prime. Okay, now what is G times O prime? It will be B by root 2. Why is it B by root 2? Because it's root 2B divided by 2. Okay, so B by root 2. So what you get, if you set the numerator to 0, forget the denominator. You set the numerator to 0, you get a cubic equation. Okay, that cubic equation can be factored. One factor is x minus 1, and the other factor is x square minus x minus 1. By the way, what is x? X is this ratio A by B that was asked in this problem. Okay, right? And the solution, as you can see, this equation is nothing but the golden ratio. You might say, what about the other solution, sir? What about x minus 1? That is the solution x equal to 1, which means A is equal to B, which means you must cut out almost the entire square and you're left with a line like this and a line like this. Naturally, if you have two lines, A into this and this one, then the center of mass is right here. So the other solution has a meaning, but it is the trivial solution. It is this solution that I am after, and it turns out to be the golden ratio. Okay. Any questions? Well, let me show you something else. And if there's still a question on this algebra, I'll tell you. Okay. So that reminded me of that circle I had seen in a village in Bihar. That wedding room, picture on the wall. They actually paint it on the wall. These women are actually village women who painted on the wall with vegetable colors. Okay, they don't even use these so-called newfangled colors, chemical colors. They do it with vegetable colors. It's called Kohber painting, by the way, if you're interested. Okay. So here is the picture, and I want to draw your attention to it. Okay. I've cut out a circle inside a circle, and I want the center of mass to be right at this point. Okay. How do I do this calculation? I know that the area of the circle is pi into r square, which I've written here. I forget that pi, okay, and I multiply it by this surface charge surface mass, which would have been sigma or rho, so that also I forget. So the pi cancels out, the rho cancels out. I have an r square. From here, the center of mass is at this point O. What is this point O? This point O is this entire 2r, small r I mean, divided by the entire 2r divided minus small 2r minus r. So 2 times small r minus r is what I'm getting here. What about the smaller circle? The smaller circle has a mass which is pi r square sigma. Forget pi and sigma. And then I have the distance go prime, which is small r. If I set the numerator to 0, divide r by r, lo and behold, I'll get the solution, which is the golden ratio. Now, what does this mean? Okay, if you have not followed the algebra, you can stop me now, or you can work it out at home. I'm saying, and there's such a simple thing that you can always work or both these things out at home. Okay, remember the square root of 2 is almost like sine of 45 degrees. Okay, it is for sine of 45 degrees. Okay, so turns out there are 2 occurrences of the golden ratio that we found. But since it is true for a circle and it is true for a square, we thought, why not investigate all kinds of polygons? Okay, so we took every even-sided regular polygon, every one of them, and every one of them has this property. But I'm getting ahead of my story. That is the universality. What it means physically is that if I cut this out in the proper, perfect proportion, in the golden proportion, then I can balance my disk on this point G. And that is what you see over here. That's a picture of me. I've actually had a kid cutting this out for me, and I'm balancing it on my knife edge, which is my forefinger. Okay, so you can actually balance it like this. That is what it means. Okay? Now, the point is, here is my square, and I go ahead and I look at this. I can make 2 kinds of excisions. The excision that we had asked in the KVPY problem was the vertex excision. Okay? But I can also make a midpoint excision. Okay? And if I make a midpoint excision again with A by B equal to the golden ratio, this point G is the point where the center of mass will reside. It will not reside inside. It will not reside outside. If I cut less of it, the center of mass will be in the body of the lamina. If I cut more of it, the center of mass will be outside the body. But there is one golden point at which the center of mass will be right on the body. Okay? So there are 2 ways of doing it, and both ways give me this. In fact, we were so amazed as we went along that when we looked at every even-sided polygon, okay, like I will not show you this calculation. Don't worry about this calculation. Even for this even-sided polygon with the vertex excision, okay, regular polygon, of course, if you look at the longer side divided by the smaller side, okay, it has to be the golden ratio for perfect balance at the point G. For perfect balance at the edge point, remember the edge point, okay, that is for the vertex excision. If I do a mid-size excision, that is to say, if I don't cut it from here, but I cut it right in the middle here, okay, as I'm doing in this particular diagram, once again, unless A by B is equal to the golden ratio, the center of mass will not be at this point or the edge point. So now what do? This is what I meant by universality. Okay, to look at any laminar body which is regular, okay, there is a universal property, and that is it can be balanced at the edge provided you have the golden ratio. So I've given physics importance, a universal importance to the golden ratio in physics, okay, and that is this particular one. It's a simple thing. It should have been known to every person after 1,000 years ago, okay. Once the center of mass was discovered, say at least after 1676, when the Principia was written, okay, it should have been obvious, but it was not. Okay. Then we look at biscalar body. Look at a rectangle. Cut out a smaller rectangle. Okay. If B by B prime is equal to the golden ratio, A by A prime is equal to the golden ratio. Once again, the center of mass will be at the edge G. Okay. Whether you make a vertex excision that I had done earlier in this particular figure, or you make a mid-size excision over here, once again, it is the golden ratio. Not only that, you look at a rhombus, same thing, or you look at an ellipse. All this we mentioned in the paper that we published in 2016. Okay, but that was not enough. That is not the only thing which I think excited the editor of that journal, which is the European Journal of Physics. Okay, what excited him more, I think, even more, was the fact that if you go to three-dimensional bodies, okay. Now I want a three-dimensional body in which I remove a small square cube out of a larger cube. Once again, if A and B are in the perfect, are in a certain ratio, okay, I'll tell you what that ratio is in a minute, okay, you can balance, the center of mass will be at the edge. Okay. Same thing is true of a sphere. Now, what is that ratio? That ratio is basically not the solution to this quadratic equation, x square minus x minus 1. It is the solution to this cubic equation, which looks very much like this. X cubed minus x square minus x minus 1 equal to 0, which has a real solution, which is 1.8. If the ratio of A to B is 1.8, lo and behold, the center of mass will be at the edge. You look at the tesseract. Now, where have we heard of the tesseract? In the movie Interstellar, which some of you must have seen. Once again, the tesseract will be balanced at the edge, provided you are at the solution of x4 minus x cubed minus x square minus x minus 1 equal to 0. There's the four-dimensional body. What is the solution of this? The solution is not 1.83, the solution is not 1.62 or something, 618. It turns out to be 1.92. Now you get the idea. If you have a large dimensional body, you will get an equation which will be like xn minus 1, and so on and so forth. The real solution to this, the one which is the fractional, or what you say, the irrational root, goes from 1.62 to 1.8 to 1.92, and it inches towards the number 2. That is also not hard to figure out. For example, if I put x equal to 2 here, this is 16, and the rest of it is 15. 16 minus 15 is 1. If I put x equal to 2 over here, this is 8. 8 minus 7. If I put x equal to 2 over here, I'll get 16. 16 minus 15 is equal to, you'll be left with 1. So you're actually inching towards this number 2. But what was interesting to us mathematically, so now we are back to mathematics again, okay, is that these complex roots have a very interesting structure, we found, okay. And let me show it to you in the next figure. What I have plotted in this figure is the real part of x and the imaginary part of x, okay, all the roots. And as you can see, say for a 16-dimensional body, these roots are all lying on a circle. And if you go to higher and higher things like 512, they make a very dense circle. Okay. So we are still exploring some mathematical properties of this golden ratio, of this equation. So now we have gone back to mathematics to explore why, what an interesting equation this is, whose real root, it has one real irrational root inching towards 2, and the other one is lying on a circle. Okay. So that is the point. So I've told you some physics and I've told you some mathematics. Okay. So let me make some, how should I put it? Let me make some concluding remarks. But let me wait for a minute. I've finished 46 minutes. Are there any urgent, any questions you have at this point about any of this?
No, sir. No questions till now.
Not yet.
So again, as Dr. Anurag Sharma said it, it's either entirely transparent or entirely reflecting, but I'm hoping it was entirely absorbing. Okay.
Yes, sir, definitely.
That is what we all hope for. So here I'm coming back to the spiral again. Okay, these are three or four concluding remarks. and bear with me while I conclude my talk. Okay, the spiral, as I said, was a favorite of Jacob Bernoulli, 1654 to 1705. It was so popular. It was so in love with the spiral, golden spiral, that he had it inscribed on his grave. Okay, and I found something very interesting. Okay, which I thought I should share. You can see this bird. This bird is approaching a prey. Okay, this bird is called the falcon. Okay, the falcon is approaching the prey, and the way the falcon approaches the prey is very interesting. It moves at breakneck speed. It's almost 100 meters per second or even more. But it goes around in a spiral and then it approaches us. Okay, as it goes around in a spiral, okay, this prey is confused. He always thinks that this falcon is going somewhere else. He looks at the tangent of the curve. Okay, so he is at peace because he thinks this falcon is not coming at him. Okay, it's called the Shaheen, by the way. In Urdu, it's called the Shaheen falcon. Okay, and but what is the falcon doing? Why is he choosing the golden spiral? He chooses the golden spiral. And by the way, if you might know, if I'm pulling a fast one on you, this is in the Journal of Experimental Biology, 2001-2002. That it's a golden spiral, and I think it is the golden spiral.
Sir, you are not audible.
Yes, sir, not audible.
Sir, voice is breaking.
Network issue, I think.
Network issue is there, I think.
Now I'm audible? Hello?
Yeah.
Yes, sir, but
Yes,
your
just
voice is
pause.
breaking.
I'll just pause for a minute. When did it start breaking? All along?
Just now, just now.
I don't know why it broke, but
Now it's
Now
clear,
is
sir.
it
fine.
clear?
Yeah, yes, sir, fine.
My microphone was away from me. Okay, so I'm holding it close. So by the falcon, okay, I'm talking about the falcon. How much of the falcon did you hear? The story of the falcon?
Just that the prey doesn't know that the bird is coming at him.
Yeah,
He's
that
going
the
to kill
falcon.
the squirrel.
Yeah, because he's going around in a circle. But the falcon is using a golden spiral.
Yeah.
And this, by the way, is in the Journal of Experimental Biology 2001 or 2. If you're interested, I'll send you the paper. I think the falcon does it because he's making a constant angle with the prey. Okay. Remember I told you that this angle made by the tangent to the curve with the center is always a constant for a golden spiral, like 60 degrees. He's going around at very high speed. If he has to keep turning his head right and left, he'll feel dizzy, or she will feel dizzy. Okay, it's usually the female which hunts, by the way. I have to tell you another interesting story about birds, and that is that the female of the species is larger and heavier than the male, for raptors at least. For raptors. Okay. Anyway, so that is what it does. And that sort of reminded me of a very famous line. I don't know how many of you are fond of Urdu poetry, but I would like to recite it here. Okay, as the finale of this very interesting session, which I have missed since morning. It is by Faiz Ahmad Faiz, the great Urdu poet. He's from Pakistan. It's by, I think this is by Iqbal. This is not by Faiz Ahmad Faiz. This is by Iqbal on the Shaheen. Japatna palatna. I mean, Iqbal knew how the falcon is approaching before the Journal of Experimental Biology. He said, Japatna palatna palatkar japatna. Lahu garam rakhne ka hai ye bahana. परिंदों की दुनिया का दरवेश हूं मैं ये शाहीन बनाता नहीं आशियाना to swerve, to swing back again. Okay, this is not for the prey. That is what Iqbal says. The Shaheen is doing it to keep the blood roiling in his veins. I am the Sufi dervish of the bird universe, of the avian universe. Okay, that's what he says. It's a wonderful poem by Iqbal, and you might want to read the whole poem at some point. Okay. So not only I would say Bernoulli, but even Iqbal was enamored of this golden spiral. Okay. There's another thing which I wanted to tell you as a concluding remark. There are other centers in physics. Okay. One is the center of buoyancy. Okay. It's a part of the body that is submerged in the water, that part ka center of mass is not the same as the center of gravity. Okay, that's called the center of buoyancy, the point at which there is an upward force on the body. And they don't always match, therefore the bodies can tend to tilt. There's another one called the center of percussion. Every cricketer or every person who has held a bat knows about it. If the hard ball, I would say the season ball as we used to call it, hits a particular point on the bat, it goes straight to the boundary and your wrist does not even feel it. The reaction is zero. A standard problem in joint entrance exam. A third one is the center of pressure, which you may have not heard about. Okay, the center of gravity is one thing, but the Bernoulli's principle, which pushes it up, might not coincide with the center of gravity. Therefore, the plane is flying in an unstable mode. In fact, most fighter planes have their center of pressure, by the way, outside the body, outside the main body, and they are always in the unstable mode. Okay, so there are other centers of mass. The center also plays a very important role. The word center, by the way, plays an important role in, how would I say, poetry. There's a poem by Yeats. Things fall apart, the center cannot hold. Here is a long quote by Black Elk, the famous last Native American Indian as we are calling it, Red Indians as we are called, last quote, before about 200 of them were massacred at a place called Wounded Knee. Okay, there's a very famous book by that name. Look at what he says. When you talk about things, you talk about the center. Okay, the nation's hoop is broken and scattered. There is no center any longer, and the sacred tree is dead. So the word center is important in literature. The word center is important to express an important thought. Okay, and this is the summary of the talk. Two-dimensional structures have been around since time immemorial. So has the golden ratio. So is the notion of center of mass. But it is surprising that nobody seems to have noticed this connection. Okay. The center, by the way, phi has been made very popular by Dan Brown. And if you just go and Google, say for example, for perfect beauty or something like that, the Blue Bella, the famous fashion giant, has declared that Scarlett Johansson is the most beautiful woman in the world based on the center of mass, most well proportioned, based on this golden ratio. Okay, so everybody is also making money out of this golden ratio. Okay. We have found systematic, repeated occurrences of this, and we have endowed it with a physics-based meaning, and we have generalized it to higher dimensions. These are the three takeaways from this talk. Okay. If there are students at 10th or 12th who would like to do some small research problem, there are some that I have in mind. Okay, and here is the reference. The original reference is by Praveen. The work is by Praveen Pathak and myself in 2016 in the European Journal of Physics. It was followed up 2 years later by a follow-up publication, again by Praveen Pathak and two people from Ahmedabad, Gautam Datta and Mitakshi Mehta. They are both lecturers. I think Mitakshi is a lecturer at a college, and Gautam Datta teaches in an engineering college. Okay. And if you are very interested on how Virahanka arrived at his series based on Pingala's work on Sanskrit prosody, there is an article just last year that I thought I should write along with a girl student, Nivedita, in the bulletin of the IIPT, March 2020. Okay. So that's the talk. Thank you very much.
Thank you so much, sir. It was an outstanding and amazing talk. It was really very good. It was a visual treat, I must say. All those beautiful pictures, so many examples of golden ratio in physics, in paintings, in structures. It was too good. Even the pictures that you shown for center of mass, they are amazing. So beautifully, everything you connected so well. So thank you so much, sir. It was indeed a very, very interesting talk, I must say. And the pictures and the, your piece of research work is also very, very, inspiring that people could think of like problems like this and they do come up with such results. So thank you so much, sir. It was as good as possible. So we are indeed indebted to you for sparing your precious time for this talk for the students and for the faculty as well. So thank you.
Thank you very much. Okay.
Yeah.
Thank you so much,
now there's
sir. Thank you so much, sir. I must say, sir, that I always say that I'm greedy for more knowledge, and I would like to tell the audience his lecture on Bombay and physics, which I heard in 2019 in Allahabad, along with his coffee table book on Bombay and physics, is mesmerizing too. So, sir, we hope to have you with us again with another another set of lectures, which are always as interesting as ever. So I think everybody agrees with me that his lectures are intoxicating, intriguing, mind-opening, and changes your perspective completely. Thank you so much, sir, for being a source of inspiration.
Yes, sir. I also agree to it, Punita and Dr. Bindal. I think we should plan more lectures. We should plan more lectures in our college for sir.
Thank you so much, sir.
Yeah.
Thank you.
Yes.
And thank you for these nice comments. It encourages me to make similar talks and do similar research work with high school and higher secondary schools.
Definitely, sir.
They're
They are
also
very
college
good.
students. Sir,
And
please.
undergraduate, first year
Sir,
undergraduate.
Undergraduate students also.
That is what
They're
I've
also
done.
they're
by
also
the way.
small.
Yeah. With basically, so far I worked with first year and second year undergraduate students. There have been only very few at the school and higher secondary school level. Okay. So anyway, yeah. First year they are mature enough at that point.
Our students will also be happy to work with you under your guidance, sir. That would be extremely nice for them.
Yes, definitely.
So they make a small contribution to the general body of human knowledge, and that is good for them, good for us.
Yes, sir, it's a service to the education. How will they, get to connect with physicists like you? I mean, this is really good.
Thank you very much. Okay.
Yeah.
Now we go to the closing ceremony.
Yes, sir. So I think we have come to the end of the online national seminar. So I would like to basically close with the valedictory note. So I start
Dr. Bindal.
Yes.
Dr. Bindal, do you allow me to show something very nice done by students?
Sure. Why not?
Yeah, sure. Yes, please.
So I would just like to, if the screen is stopped from sharing, then probably I can.
I think it's stopped from sharing. Yeah. Why is that? Yeah. Why is this? I just
down or up?
Stop sharing my screen. Just stop
no, sir, it's okay. No, it's okay, sir. We can see you and your screen is stopped from sharing. So that's not a problem. So, sir, with your nice presence in our department today, and it's a webinar, I present to the people who have gathered here, the teachers, the faculty, and the students, the magazine made entirely by our students. Here you can see it, Microcosm, exploring the universe. This magazine has been compiled by the students of BSc Physics Honors and BSc Physical Sciences. They have made their own group and they have done their own research and they have tried to come up with a magazine. This was also in force earlier, but now it will be there for every month. And they have had several components in it. And here is also Indian heritage. So there is a section of Indian heritage. There is a section of career counseling. There is news flash. There is so I shall just go to the next page. And as you can see, they have found out who are the people who have done different types of things. There is a detail about our senior most teacher, how she joined, and that's inspirational to our students. There is there is an article about Indian heritage, and then there is about career corner, job opportunities after physics honors, all the institutes that are there, AFR, Homi Bhabha Institute, IACS, etc. There is a list of all possible courses they can enter into, academic courses, and so on. And then articles about expansion of the universe, Hubble's law, and what all is very famous these days, gravitational waves, and so on. Matter, antimatter, annihilation, and so on. So these were the topics that they chose for this month's magazine, Comet Neo-Wise, as you can see. And then there are further fun activities also. There are lectures on, there is a section on entropy, relativity, then virtuosity. All that you can see here has been done entirely by the students. And no help. So this is these are the paintings made by the students of our department ourselves. Some computer science students have also pitched in. So this is to develop the ambience of science and culture, and the culture of quest for knowledge. There are crossword puzzles also, and there are questions and so on, riddles, etc. So, and that's the team. And I just wanted to display it so that it is inspirational to the students to see that all the teachers are watching, that they have done hard work this month and shall continue for each month, as they have a complete team working on it. So that's it. Thank you so much for giving 2 minutes to me, Dr. Seema and Dr. Bindal. This is the work of our students.
Yeah. Thank you, Dr. Punita, for showcasing that. So
Thank you
now,
so much.
now we come to the valedictory session. So I begin formally. So respected Professor Ghatak, Professor Anurag Sharma, Professor Rajaram, and Professor Vijay Singh, who is right now present with us, and dear participants. I, Dr. Pushpa Bindal, welcome you all at the valedictory ceremony of the online national seminar, Exploring Physics with Experts, organized by Department of Physics, Kalindi College, and sponsored by Nasi Delhi chapter. This seminar was organized with the motive of giving young undergraduate to university students a flavor of physics at its very best, from the very best in the field, so that they could get motivated and learn to enjoy it. Faculty too revised their basics coming from these eminent physicists. The participants have benefited a lot. It is evident from the comments and the feedback which has been received so far. In a way, these online seminars are a boon in disguise. It has given an opportunity to the students and faculty from different states to come together on these platforms without an actual travel and much expenditure involved. We had 242 registrations, out of which roughly 200 are students, and these are from different parts of India: Delhi, Bihar, Haryana, Himachal Pradesh, Jharkhand, Karnataka, Madhya Pradesh, Punjab, Rajasthan, Uttar Pradesh, Uttarakhand, West Bengal, Telangana, Odisha, Madhya Pradesh, Kerala, and Kolkata. And they have attended the national seminar via Zoom link and also the YouTube channel of Kalindi College and Nasi Delhi chapter. Huge participation by students and faculty signify the huge success of this seminar. Discussions that have followed by each talk, they are also really great. So I would take this opportunity to sincerely thank Professor Ghatak and Professor Anurag Sharma to have faith in our endeavors and sponsor the seminar. I extend my heartfelt thanks to all the resource persons. They have spared their precious time for this seminar. I extend my heartfelt thanks to also the Principal Madam, Dr. Anjula Bansal, for supporting all the initiatives of Physics Department. I thank the faculty members of my department who are also members of the organizing committee. Dr. Rachna Kumar, Dr. Punita Verma, Dr. Trinsa Srivastava, Dr. Rashmi Menon, Dr. Mazhar, Dr. Arvind, Mr. Ankur Anand, Dr. Savita Sharma, and Ms. Varsha. I am so thankful to all of them for devoting time in making all the arrangements along with taking their scheduled classes. So just as all good things come to an end, we have come to the end of this seminar. Now I request Dr. Seema Gupta to take over and formally close the session.
Thank you, Dr. Bindal. Thank you everyone for being the part of this national seminar. I'm sure that the students are the one most benefited by all these lectures, and also the faculty members. Simple concepts of physics explained in such a beautiful manner. That was the beauty of all these talks. I look forward to arrange more of such lectures in our college in future. Thank you everyone. So with this, we announce the formal closing of our national seminar.
Yeah, the feedback link is once again shared in the registered email IDs for all participants. So kindly fill that up so that we can process further.
Yes, it's necessary to